Hi, sorry to interrupt. Could you please turn on the mic so we can hear via the Zoom chat? I mean, via the Zoom.
So I can use the microphone of the computer and not of the projector. So is the microphone good?
Potentially, I can hear you at least. I hope I can hear the speaker.
So
Yes, yes, I can hear you. Yes, thank you.
I have to speak to the computer.
Thank you. Perfect.
So, I was saying, what is important is that the transformation that we are considering respect the order of the on R, and so what we are doing. So we consider any. So we will. We consider measures that are supported by random homeomorphism. We will see different. I will give a general hypothesis where we will have a uniqueness, but to keep in mind, there are some examples to have in mind. One is the random walk on R. So if you consider Cn just to be a translation, plus minus one, so you have a homomorphism that respect the order, and so a random walk on R, in some sense, are an example of what we want to prove, and you see that is the best example to prove uniqueness. So we will need to have a hypothesis that avoid to have a random walk, because in this case you can have several invariant measure for that. Good example is example where you have some contraction of the space. You can contract your space R, and for instance, where the Cn are affine recursion, in the sense that you have some translation, but also some term that may contract your space. Sometimes I'll conjugate R to the interval in order to be able to plot things easier, mainly what happened at the endpoint. And so that so there is a natural conjugation between the group of homomorphism of the real line and the group of homomorphism of the open interval that fix the endpoint. So this is make sense. So for what we are talking about, we will concentrate in the case that we take a measure on the homomorphism of the real line that is discrete and possibly finite. For what we do, this is the main setting. So you can think about taking two random homomorphisms and multiplying this and asking whether there is an invariant measure and when it is unique or not. This is the question. So we will be looking in a situation where the Markov chain Xn of X generated by this random recursion is recurrent. I mean, recurrent in my setting means that there exists a compact interval, big compact interval, that is visited infinitely often, whatever point you start. You take a big interval, and whenever you start, you can start anywhere, and then the probability to visit this interval infinitely often is 1. So typically, if you take a random walk on R, centered, you have something that visits infinitely often a large interval. So in this situation, there exists, it is possible to prove, since the transformation psi are continuous, that the Markov operator, the Markov kernel associated to the Markov chain is conservative, and that there exists an invariant measure that is random, in the sense that it is finite on compact set. So and being invariant is the same of a probability being invariant, in the sense that if we start with this choosing the element according to this measure mu that may be infinite, and we may let the group act with a measure mu, we recover something that has the same distribution, but this distribution can be infinite. It's not necessarily a probability. So, but it's finite on compact set, so it's reasonable to look at. So, example, easy example that one can have in mind is for the random walk plus minus 1/2. You have the counting measure on Z is invariant, but any translation of the invariant measure on Z is invariant. You stay on the, so you have an infinity of invariant measure on infinity of an invariant measure for the random walk, for this random walk, and any invariant measure that can be constructed integrating such a measure, such as, for instance, a Lebesgue measure, is also invariant. And there are cases where you have a unique invariant measure, so it can be quite easily proved that if your transformation are Lipschitz and they contract in mean, then there exists plus some moment condition that they say that you do not translate too much too far away. Then there exists a unique probability measure on the. So the situation can be quite different, and we want some criteria that guarantee uniqueness or to understand how the invariant measures are for such systems. So if I go on, I wanted to give some conditions that ensure recurrence, and so the existence of the invariant measure. So that it is well known that for the affine recursion, the fact that the existence of the invariant measure is related to the logarithm of the AN, that is the Lipschitz the Lipschitz constant of such a transformation. And so if the logarithm of A1 is less than 0 in mean, then we know that there exists a finite invariant measure. And if it is equal to zeros, we know that there exists an infinite invariant measure. It is recurrent, and you have an infinite invariant measure. Such a result can be generalized to other systems. And what is important is that what happened at the end point. So if, for instance, you can have a result of the kind, if you take diffeomorphism of the interval 0, 1 that are differentiable on the end point, and you suppose that the measure is a finite supporter, for instance, do not have a problem. If you have that the derivative at the endpoint is in mean bigger than 0, bigger or equal to 0, you have a recurrence. And the measure is finite if it is, this derivative is strictly positive on the both sides. And if at least one side is equal to 0, this measure is infinite. So what you may think is such a system, and where the derivative at endpoints is sometimes certain. Okay. So what is the goal of this of our paper? Is was to find conditions that ensure that the measure that exists is unique, and if it's not, to characterize what are the different ergodic measures, or maybe on the other way, characterize ergodic measure of the system, and then deduce condition where it is unique. So this has been a question that has been explored in several directions by several authors. I put here some paper that, in some sense, were the more inspiring to us. For the classical Choquet-Denis theorem is, in some sense, is a comfort result on this direction that say that whenever you have a translation that do not have a discrete do not have do not fix. There is no discrete closed subset that is fixed, so it is not periodic. Then there have a unique invariant measure. So the only situation where you can have several invariant measures is that you have a measure with discrete support. And then there have been several results for the case that the measure is finite. So there are conditions, as we've seen, where the map are contracting in some sense, can be Lipschitz, can be a fine map, or more recently, there is a nice result of Malisset for general homeomorphism of the circle, where it proved that any non-trivial, let's say, if you accept some special case, homeomorphism of the circle have some exponential contraction property and have uniqueness of the invariant measure. The situation where you have not have this strong contraction property, and you have an infinite measure, is more delicate, and there is a paper of Babio, Bouger, and Lee, where they study uniqueness of invariant measure of random affinities in this case, and they prove a nice property of local contraction that say that if you look at the system, if you look at, you take two trajectories and let them evolve, that's two trajectories that start from different points. So you take two different points, y and x and y, and you apply the same trajectories, and you look what is the difference, what is there you do. And when you have in the situation of a fine recursion where the n is centered, you do not converge. So the two trajectories may be very far away from one from another. But if you look at the two trajectories through a compact window, so you don't look at what happened far away, then what you see is something that is contracting, and the true trajectory through a compact window converge one through, so the distance between the two of them converge to zero. So there is some local contraction that are enable to prove uniqueness of the invariant. But the paper that was was motivating to us is a paper of Derwan, Cleftin, Navas, and Perwani, where they prove the uniqueness of invariant measure for a symmetric measure on the group of homeomorphism of R plus. And so what we wanted to do was to get rid of this symmetric property that appeared to us not to be natural, and was I always have some application in mind, not very suitable for application. And so the uniqueness seems to be a much more general property. So we wanted to see to get rid of this symmetric condition. So the hypothesis that we need to prove uniqueness of an invariant measure supported by all R are mainly two in place of recurrence. The first one that I call unboundedness. The system is unbounded in the sense that it can reach any, can go through toward minus infinities and toward plus infinities. So if you start to any point, you look at the semi-group generated by the support of the measure, the infimum of the orbit is minus infinities, supremum of the orbit is plus infinities. And this property is also very nice because you can easily check it on the support. It is equivalent to us that any point can be pushed on the right and pushed on the left by some element on the support of K. If you take an element, there is any element, there is an application on the diagonal that is on below, and the other is above the diagonal in this point. It's quite very easy to draw application. So, and this prove that this hypothesis needed to guarantee that the support of the measure is all R, and in particularly one first consequence that is forbid to have points that are fixed, because if you have a fixed point or fixed point that is fixed, you will it is not possible to have uniqueness because you will separate your R into half a line, and you will have an invariant measure on the left and invariant measure on the right, and then you will have two separate invariant measures. So if it's unbounded, you don't have a fixed point, and so at least you cannot separate your R into half line.
You ask something, so it's a very natural kind of possibilities, but suppose you are not bounded, and suppose you don't have this fixed point, isn't it natural to expect that you will have uniqueness as well?
This unboundedness is not crucial. We wrote it like this, but then we realized that this is not really what is important. What really is important is the second one. So this is, you could have a much weaker condition like this on the. So, but what's really crucial is that you have some contraction. So you have a compact set, E, such that any other compact set can be shrinked inside E for some power of some element in the same group generated. So it's possible to take a large compact and put it in in a small box, in a reasonable box. That is the same for all. So this is typically a property that fails on for translation. So you cannot, you should not. And so under this hypothesis, so you can prove that there exists so any discrete measure on a recurrent unbounded contracting stochastical dynamical system defined by the discrete measure on homeomorphism mu admit a unique invariant random measure on the system. So this is quite general. Do not have moment, but the moment is hidden in the recurrent. To prove recurrence, often you need moment. So you need some moment, the condition, if you want to check this hypothesis. And if you want to have some easy applicable criterion, for instance, for diffeomorphism of the interval, you have to prove recurrence, as I said, you can have to guarantee that is repulsive on 0 and 1. Unboundedness is this, as I said before, you can push on the left, on the right every x, and contractness in this setting you can be, for instance, proven if you can guarantee that there exists a phi in the semigroup generated by gamma that is repel at the same moment on the left and the right. So both are repelled in the. So under this hypothesis, then you can guarantee that there exists a uniqueness invariant measure of on 0, 1. So, okay, so this is our theorem of uniqueness, but so this result is a consequence of a result of characterization of ergodic measure of the system. And so I want to spend a little slide on explain what are invariant measures in this setting and why they are the fundamental brick that build invariant measures. So we say that a measure is ergodic if for any invariant set of R, that is a set that if you translate it with any measure of the support of mu, you stay the same modulo the measure. If you have a such invariant set, then the measure is ergodic. Whenever such an invariant set are trivial in the sense that either it is 0, either the complementary is 0. And so typical case where you have so if you take the example we have seen before of Cn being the transformation plus minus 1 with probability 1/2, it can be seen that the counting measure on Z, V on the integer or the integer shifted by A is ergodic, while if you take the Lebesgue measure, it is not ergodic because you can take any set that is invariant by Z. That is this is not trivial, is invariant but not trivial. Okay. So another way to say a measure is ergodic if you cannot restrict it to a subset obtaining an invariant measure, another invariant measure. An ergodic measure cannot be restricted, cannot be restricted to a set obtaining the smaller invariant measure restricted it to the subset. So if you take a subset A such that the restriction is still invariant, then the measure that you obtain is either the measure that you started with or the 0 measure. So ergodic measures are the fundamental brick you use to construct invariant measures. So you have in the case also, any invariant measure can be written as an integral of ergodic measure. So this is quite common result in the case mu is a probability, but can be extended also to infinite measure, at least in this case. And what is nice with ergodic measure that you have some sort of Birkhoff ergodic theorem, and that you can control the number of visits on set. So if you take F and G to compactly supported measure, let's say that are the indicator of some set F, some set G, and you look at the ratio of the number of visits in F and the number of visits in G. So you count the number of visits in F and the number of visits in G. Then this ratio converges on the ratio of the two sets for almost every starting point, almost every starting. So this is the equivalent in infinite measure of the Birkhoff ergodic theorem. In Birkhoff, when you have mu is finite, you can take G to be the whole set and you have N here. But for invariant measure, you have to take the ratio in order to have some convergence. And so this is the main ingredient. So characterizing ergodic measure, unable to characterize all invariant measures. So whenever. And so what I think is the nicer way to write our result is the following. That say the following results that say that ergodic measures are determined by their support. So if you take a measure, we can define the closest support of nu being the smallest closed set that has measure 1, that is a full measure 1, or equivalently that is the set of all points that are whose for which every open neighbor of X is as a positive measure. Donc this is a closed set, and it can be proved that is gamma invariant. That is for any element in the support of mu in gamma, phi of the support of nu is still contained in the support, because is the support of invariant measure are closed gamma invariant set. So what we can be proved that if you take two invariant measures, then if their support coincide, then they are the same. So the support characterize the invariant measure. And furthermore, that if the only possibility for an ergodic measure to be the support of an ergodic measure to be strictly contained in the support of the other measure is that the smallest one is discrete on R. So the only obstruction to the fact that to uniqueness in some sense is the fact that there exists closed discrete gamma invariant set. This is like the case of the translation that we have seen before. We have a lot of discrete gamma invariant set. But if you cannot have discrete gamma invariant set, then ergodic measures are characterized by their support, and so if you can see that there exists a unique gamma invariant set, then the measure is unique. This is the way. So in particular, so minimal closed gamma invariant set are the support of a unique ergodic measure. But there exists ergodic measure whose support is not minimal, since it may contain a discrete set. This was quite surprising to me, but if you think a little, you can construct easily an example of ergodic measure that have no minimal support, putting together some transformation that has a unique probability, a counting measure, or a translation plus minus 1, and then you can construct an example that figure on the interval that fix z. So an example like this. So you have two transformations that fix the integer. So the counting measure of the integer is an invariant measure. And then the probability measure that then if you quotient on the interval, you have an invariant measure on each of the intervals. Then you can duplicate it on all of z, and this state to be invariant. So you can have invariant measure, ergodic invariant measure whose support is not minimal. But this is the only possibility, that is there exists a discrete measure inside. Okay, I wanted just to give some idea of the proof. I still have 5 minutes, okay? Just to give some idea, so what we use ratio ergodic theorem to prove that two measures are the same. What I need to show that if I know that if I take two ergodic measures, mu1 and mu2, I know that if I start from almost every point x1 chosen by according to mu1, I convert to the ratio given by the measure mu1, and if I start for mu almost a point x2 chosen according to the measure mu2, I convert to the ratio given by mu2. To prove that they are the same, I need to prove that these limits are the same. So that for any x, if I choose an x1, I can choose an x1 and x2 in each of them, that they give the two limits. So if the support are the same, I will be able to choose x1, x2 very close to each other, because they are on the same support, and so I can choose them very close to each other. And what is the idea? So proving that, so what I do there is I take an interval a, b, and I want to count the number of times my Markov chain starting from x1 is in AB. So this is the composition of the maps C1, Cn applied to x1. So since the C1, Cn are invertible, this is the same on asking that and preserve the order. This is the same of asking the x1 is in the interval given by the reverse transformation on the other side. So what I need to count is the number of times x1 is on the interval given whose left extreme is the image of reverse image of A, and the other one. So you have this interval, and I have to count how many times x1 is in this interval that is given by the reverse system. So the good intervals are the one where, and the same for x2. So if x1, x2 are both inside, then the difference of between these two ratios will be small. The situation is when this interval only overlaps one of the x1, x2, x1. So we have to reduce, control the probability that this taking x1, x2 sufficiently small, close to each other. And so this can be done since we can control the property of the reverse system, the one constructed by the reverse map. So there are different arguments according that the reverse system is conservative or dissipative, but in both cases, we can control that this situation appear not very often, and so with probability smaller than one, is sufficiently smaller than one since it converges, and it is and then guaranteed that the two this rush should converge to zero. So this is the main idea of the proof. Just to conclude very quickly with some ongoing work that what I'm working now. So there are two ways that we try to explore, to generalize. So one thing that I, in this moment, quite interested in what happens when PCN are not inverted, are not in a group anymore. What happens if we have a non-invertible map? Still, it's possible to give some criterion of uniqueness. So we have an ongoing work with Thomas Arek and Anno Pelmai. We're just finishing to read it, so it's almost finished. But in where we try to explore what happened in some situation, if we have a non-invertible map. We take these two maps, one half and one half, and we try to see if there exists a unique map for this. So we have example where the uniqueness does not hold, but for this one, we can guarantee that this unique since it mean injective. But what is really important is not that there is the maps are injective, but just that in mean each point has at most one preimage. So in this system, each point can have two preimage with alpha, one preimage, zero preimage with beta, but since there are half and half, it means they have less than one preimage. And so under this hypothesis, we can manage to prove uniqueness for such a system. Stationary probability. For this paper, we do not we just able to deal for the moment with probability measure, not infinite probability measure, just probability measure. The case where you have a positive equivalence, so you reflect strongly reflect on the end. And this is, and the other situation that I'm exploring, this is with Marc Peignet mainly, and the CAM is the multidimensional case. So for the moment, we are looking at affine recursion. So we have a result of uniqueness in the case that the n are positive, and they are making progress in the general case. I think maybe by June, maybe something is really be right. Thank you for your attention.
I have a question. So your book is about homeomorphisms. Something in dimension two.
So what I was saying, yes, no, yes or no. it's important that you have an order. So the argument there do not work for a higher dimension. We can expect something for more rigid transformation like affinities.
And even the island doesn't work, but also you wouldn't have the uniqueness no longer, or in general, or it's not clear.
It's not clear. It's not clear to me. You can I think it can be become very wide. If you so the one and its co-author tried to explore something that was more general, order preserving transformation on more general space, and I think this argument can go through in this kind. Not the measure preserving, the order preserving.
So you mean maybe even for much larger spaces? So the essential that you have, it's order preserving and maybe.
Yeah. This is the